Today we're going to talk about loads reconstruction, and we're going to go through a brief introduction on the goals for basically early design and then the need for loads in doing those analyses. We'll look at ways to recover loads traditionally and then look at the loads reconstruction using measured strains. We'll talk a little bit about strain gauge placement in terms of placing gauges at ideal locations, and then we'll finish up looking at the application of loads reconstruction in dynamic analyses. The way to develop good products is to go in and to do early design. The idea being that we cover a large range of design opportunities before we ever commit to parts. The more that we can actually understand our designs up front basically reduces issues downstream. Now, there's a major issue with this in that in order for me to go in and to do detailed analysis, especially for fatigue of early designs, I have to understand the loads going onto my part, which obviously don't exist yet. And so I need to somehow estimate those or possibly reuse those from previous designs. That's what we're going to be looking at. When we have a component and we measure strains, the strain histories we recover have basically a fairly short shelf life because they only belong to that one part. They tell me about that part's structural response. That means I really can't use those strain histories downstream on the next design because the part basically, as it changes, this response and hence the strains will change. If I'm actually able to go in and recover time histories from those strains, those load histories that I recover basically can be applied downstream to a new design. The loads won't change on the new design. It's the same loads that were applied previously. But the strain histories obviously are a response of the new structure. So if we can turn our strain histories into load histories, we have the ability to go off and use them in our early designs. Many times the loads that we're looking at, well, obviously cannot be measured directly off the new design because it no longer exists. And at times we have to go off and to estimate what it is. Secondly, even in a traditional sense, it's very difficult at times to measure loads because whatever I basically insert to measure the loads changes the load paths. So if I want to know the loads on a particular component, I may end up changing the load path, trying to put in things like force transducers into the structure. We're going to look at trying to turn the component we're interested in into its own force transducer. And the way we do that is basically by leveraging the fact that as I apply loads to a structure, the structure basically is going to respond. Each set of loads can generate a unique set of responses on my structure. If I have a linear system, I can go in and take those individual responses and I can basically linear superimpose them to basically predict the final structure's response, and knowing that I can back off what the individual loads had to be. Now, in order to do this, it requires the proper number and placement and orientation of gauges, but we'll talk about how we can actually do that. Traditional force transducers, systems that we would use to go off and measure loads, are custom built to try to extract out a particular loading and basically ignore all the other loads coming in. the way that you use them is you would go in and either replace a part or try to place them into the load path adjacent to the component you're interested in. Problem with that, obviously, is that these many times will alter the load path. Now, these actually are extremely accurate. They have tremendous linearity across the load range. They, again, are been custom designed to pull out a particular loading in the system. But again, many times they're inappropriate for what we want to do because there's no way for us to put it into our system to measure the component load without changing what those loads are. However, if we go back and look at what these transducers do, and here what they're actually doing is they have a set of strain gauges properly placed to go in and to extract out a particular set of loads. For example, here I have a simple cantilever beam, and I've got several loads on this, axial and a moment load, and I've placed on here two strain gauges, a strain gauge at the top surface and a strain gauge at the bottom. By going in and combining those strain gauge responses in the proper way, I can extract out first the axial load. If I just take the gauges and I sum their responses, what I'm doing is looking at the axial load independent of the bending load. If I basically took those gauges and I difference them, I create a bending bridge rather than an axial bridge. I'm now looking at the bending response, not the axial. So there's ways that I can go in and configure measurements on my structure to pull out individual components. If I looked at those previous equations, I could actually rearrange those, and instead of predicting the loads on my structure, I could say a particular load generates a certain response on my strain gauge. And so just rearranging those equations, I now have expressions that describe a strains response to an applied load, which is what I really want to do. And if I go in and have a linear system, I can superimpose those two responses for my upper strain gauge, one from the force, one from the moment, and now be able to describe a strains response in terms of those individual applied loads. And here I have the expressions both for the upper gauge and lower gauge on my cantilever. Taking those equations, I could just put them in matrix form. So now I have exactly the same equations we saw earlier, however, in matrix form. But in matrix form, now we can see that what we end up with, those coefficients that describe the relationships between strains and loads, are in essence a matrix, a sensitivity matrix. And it's possible for me to go now solve that set of equations, and now I can go in and basically recover the forces from the applied moment, from the applied strains. So technically, we have a path that we can go in, measure strains, and recover loads. It's quite not that simple. The first thing is that ideally on the cantilever beam, I could go off and write equations out of engineering mechanics to do those relationships. What do I do when I have my actual structures that aren't as simple? How do I actually get that information out? Well, we can still use the same sort of approaches where we're looking at linear superposition of responses. And so on here, I have an arbitrary structure, and I've got two loads on this structure. I'm also measuring three sets of strain responses. And if I look at it, for every strain response, I can go off and estimate what influence that load has on that strain gauge. Hence, I can come up with a sensitivity for a particular gauge to a load. If I go off and assemble those, I can create a sensitivity matrix that basically describes for each load that I apply to my structure what the impact is on each of the gauges. Now the question is how do we come up with this sensitivity matrix? One approach would be to go off and actually have a physical part, fixture it, apply loads to it, apply gauges, and measure the responses for the gauges. But again, what we're looking to do is basically get this information up front prior to having parts. So another approach to this is to use the virtual strain gauge inside of DesignLife. Inside DesignLife, I can have my part represented as a final model. I can place virtual strain gauges on my model and apply individual loads, unit loads on my structure. These loads will correspond to the actual input loads coming into my structure in the design. And what comes out of virtual strain gauge is going to be a response for each load case for each gauge. It's that sensitivity matrix. So what we're looking at here is the output. I've applied 2 load cases inside of DesignLife. For each load case, I get an output for my virtual strain gauges. And so I've basically produced this sensitivity matrix virtually out of DesignLife. So we have the sensitivity matrix, and again, we saw earlier on how we could put together a relationship between loads and strains. What I have now is a little more accurate description of that. So I have my loads coming into my structure. I have the sensitivity matrix I can get out of the virtual strain gauge off of my FE model, and I have the measured strains. Now you'll see that there's a term in here that we hadn't talked about before, and that is the strains that are measured are actually have errors associated with them. Basically limits on how low a strain they can measure, additional errors that may come in from misplacement of the gauges and things like that. So the complete equation is not only my sensitivity matrix from DesignLife, loads going in, but there's some additional errors on my gauges we'll come back and talk about later. The other thing, if you had noticed on my previous example, was that my sensitivity matrix wasn't square. I had more strain gauges than I had loads going in. And so my simple assumption of going off and inverting that doesn't work. And so what we're looking at now is taking this system and somehow solving for L, knowing S. However, I can go in and rearrange those equations. And if I were to go off and take my sensitivity matrix, take the transpose of it, so basically replace the columns with the rows and pre-multiply this equation, I can go in and now rearrange the equation, and I end up with a system I can solve. If you look at this, I have taken what I need to invert, and I've got my sensitivity matrix multiplied by its transpose. That makes it square. Once I have a square matrix, I can go off and solve that directly. And so I now have a relationship that is the strains through this combination of calculations on the sensitivity matrix to my loads. And you'll notice that the loads have this little cap on it. What these are the load estimates. So again, the estimated loads from my measured strains. If one were to look at this term, the A transpose A, the inverse times A transpose, that actually is a least squares fit. I'm going off and generating a least squares fit of my loads from my multiple strains. So this is the approach we're going to use. And what we have done is created a process inside DesignLife that goes off and actually is capable of taking an FE model with virtual strain gauges, taking a series of measured strains for those gauges, and predicting the sensitivity matrix, and then reverse engineering the loads from that. The top portion of this flow is the virtual strain gauge that we saw earlier. So basically I have my FE model. On it, I have a series of virtual strains, and I have a series of load cases in that model that represent the loads on my structure. And the output of this is going to be, for every gauge, a response to every load. Those are passed in to the loads reconstruction glyph, and it brings in that sensitivity matrix, and it also brings in a set of measured strain histories that were measured off at the same locations, same orientations on the structure. And it goes through that linear algebra that we saw on the previous slide, takes the measured strains through the combination produced by the sensitivity matrix, and basically estimates the loads. And so our output are a series of estimated load histories. And then we'll see next few slides, we have the ability to go in and not only estimate the loads, but to estimate errors on those load estimates, as well as come back in the lower section of the flow, take our measured strains and overlay them on top of our predicted strains from our predicted loads to look at whether or not how accurate our how accurate the numerics are in our estimate. We're going to go back and take a look at the equations just quickly and now talk about the error estimates. I had mentioned that when we looked at the equation that represented loads to strains, there was a term that we ignored initially, and that was that every gauge has a set of strain errors associated with it. And then we used basically just that standard equation in our estimate to generate our estimated loads. Now, the loads in the first equation are the real loads on the structure. The loads in the second equation are the estimate of the loads from the strains we used. What we can do here is actually take and replace strains in this, the vector S in this equation with the term up from above. So now I have a large equation that goes off and relates loads, both the estimated and the real loads, with respect to the error estimates in the strains and the sensitivity matrix. And if you go through enough manipulation of this equation, what you can end up with is a equation that goes in, and this variance of L cap is in essence the load errors on my estimated loads. So it is an assumption of the errors on the loads I've estimated, and it is actually described by two terms. Sigma squared here is the variance on the strain measurements, and it's calculated from our estimated errors on our strain gauges. And then A transpose A is basically the sensitivity matrix. And so what we're looking at is our load estimates have errors associated with those that are, one, a function of the strain measurements, but also is a function of the sensitivity matrix. And that sensitivity matrix is basically, it is described by the number of gauges that I've used in my model, the directions and positions of those gauges. So what I can do is look to position my gauges where, one, I minimize the measurement errors to begin with, but two, I have placements that give me the best. What I'm trying to do here is place gauges that for each load case, I'll end up with a very unique set of strains across my gauges. That's kind of the fundamental assumption here, is that for each load case, I'll end up with a unique set of strain measurements off my gauges, and with that those sets of unique strains, I can, because of superposition, I can extract out what the loads are. So now again, we have this quandary: how do we get to the right number of gauges? Where do I place the gauges, and what orientation do I put the gauges in? And what we're going to do is look at the numerics of that sensitivity matrix and try to basically build a sensitivity matrix from a series of gauge locations, orientations, and positions that give me the best numerical response. And in essence, that's giving me the ideal locations for the gauges. To do that, we're going to go off and look at, across our model, every location that we assume we can put gauges. We're going to then go in and look at combinations of those locations and orientations, and from that, pick the best location. That's actually the purpose of the strain gauge placement glyph. What the strain gauge placement glyph does is it brings in an FE model, and this FE model has applied to it every load that I know is going to go into my component. And this is actually very important. If you miss a load, you're going to go in and not generate a valid set of load estimates, because we've taken strain responses from the structure that came from a load that was never included. So the key aspect of this is, one, to have a load case representing every load going into my structure. Secondly, we go in and identify locations where we can't put gauges. On almost any part, I want to have places that are covered up because of clamping, fixturing, bolts, things like that. So we identify places we can't put gauges. And then what the strain gauge placement glyph does is go in and look at generating a series of gauge locations that would give it the best response in terms of the sensitivity matrix. The stronger we make that sensitivity matrix, the better our estimate of the loads will be. And we actually do this not for a single set of gauge locations. The gauge placement allows me to go in and run from a minimum number of gauges up to a user-specified maximum. The minimum number of gauges is actually the number of loads. I have to have at least as many gauges as I have loads to actually recover the load histories. But then additional gauges actually give us more confidence and a better estimate on the loads, because again, this is a least squares approach. The more degrees of freedom I have, the better understanding I have on the errors in the structure. And the output now that comes out of the strain gauge positioning is, if I had specified, actually in this case here, I have on my bracket 4 load cases, the minimum number of gauges that I could use are 4. I've also specified in the strain gauge placement that I wanted a maximum of possibly 6. It's gone off and calculated estimates for gauge placements for 4, 5, and 6, and I have virtual strain gauge sets out on the system that I can apply inside DesignLife, and I also have some statistics coming back and giving me some information about that. While we're here, just some of the information coming out is qualitatively useful, but not quantitatively. What we're actually doing for the sensitivity matrix is we're trying to maximize the determinant. And from a linear algebra point of view, in order for me to go in and invert that matrix, the larger the determinant, the better the mathematics are. And so we're looking at trying to come up with combinations that maximize the determinant. It's basically a d-optimal solution. But again, the actual value of the determinant we don't care about. However, there are some parameters coming out at the estimate as well. These are variation inflation factors. But what they're really useful for doing is, again, we're trying to find unique combinations of strain gauge responses for each load case. And what these are giving me an estimate of is whether two load cases are generating very similar strain responses. If I have large numbers in these values, what they represent is that two or more load cases are some sort of scalar combination of each other. And if they were exactly a scalar combination, then it's impossible to solve. Because when I'm going off and solving my matrix, I'll end up dividing by 0. So these are actually useful in going off and getting an understanding of whether I have applied loads that are purely unique to my structure, or maybe I've applied a load that basically is just representing another load that's coming in at the same time. Once I have a set of gauge positions, again, I can go through the loads reconstruction. Let me get out of here now, and I'm going to go in and open up DesignLife and run through a quick demo of these inside of DesignLife. Okay, I've opened up DesignLife. I'm in a directory where I have an existing process and models and loads. And so I'm going to go in and open up strain gauge process here, the placement process. And it literally is a very simple process. I have a model coming in, and it's going to be this bracket. And in this bracket, I have a series of load cases. Again, as I said, the key to this is to have a load case for each applied load in my structure. And so this particular structure, the base is bolted to a fixture, and I have a mass sitting out. Shift this here for a second. I have a mass sitting out from this that's actually connected with rigids to the upper bolt locations. And so that mass is excited due to accelerations in different directions. And what I have here, I have accelerations that are being applied laterally, fore aft, and vertically. So I have these different loads coming in to the structure, and each one of these loads generates a unique set of stresses on the part. So I have those. I have my strain gauge positioning glyph, and if I look at it, I've got properties for it, and the properties are, one, getting the data in from the FE model. And so I have here the fact that I have a model coming in, I have stresses coming in from that. I have a couple controls on this. On that particular part, or actually any part, there are locations where I can't put gauges because of the physical geometry. I can't put gauges near the edges of the part because they're at I won't have material there. I can't put gauges where I have sharp radii or curvature. And so we have controls here where we can specify breaks between elements, this feature angle, and this is this 20 degrees here is basically if I have two edges of elements coming together and they form an angle that is off of 180 degrees by more than 20 degrees, it won't let me put a gauge at that node location, just because it's going to be a hard edge. There's also a radius of curvature that specifies if I pick a location for a gauge and I've got curvature that is a smaller radius than that radius of curvature, it won't let me put a gauge there either. So it's going off and identifying portions of the model not to place gauges. In addition, I've brought in a list of nodes that I said you're not allowed to put gauges on, and what those are locations around my mounting point for the fixture, as well as the mounting locations for my component that's attached to this bracket, where again I couldn't put gauges because of the fixturing. And then finally, down below, I have specified a number of gauges, a max number of gauges allowed to actually compute. So if I go off here, take this model, I have again my sets of stresses, I have parameters in the strain gauge placement. If I run this, it actually goes through an optimization where it's looked at every possible location and direction on that model, and now has produced 4 different sets of gauges that I